Okay, thank you. So in the next session, I'm going to explain how to push these techniques even further to design MPC protocols. Okay, so let me give you a little bit of overview about MPC. So a classic approach to run a private distributed computation is to rely on a trusted party, right? The parties can send their inputs to the trusted party. That party will compute the function and will spread the output. And naturally, there are a lot of disadvantages with this approach. For a start, the parties need to find a party that they all agree to trust. It's one point of failure. It could be corrupted. The behavior of such a trusted party is not monitored. So there are many, many issues working in this setting. And secure multi-party computation is about removing this trust. Instead of working or approaching this trusted party, the parties can communicate directly. And as I mentioned before, we distinct several settings. We have active versus passive versus active adversaries, and we have honest majority versus dishonest majority. And in this talk, I would like to focus on the strongest attack model of proven security in the presence of an active adversary in the dishonest majority setting. And our goal is to design a practical and also scalable MPC. So the word scalable sort of repeated in the second talk a lot. And MPC actually has also issues of scalability. And the main problem is when we grow with the number of parties. Okay, and similarly to zero knowledge, MPC has many, many, many important and useful applications. In the context of blockchain, you can use MPC to design private smart contracts, auctions with private bids, also setup ceremonies, which is quite useful, not just for zero knowledge, also in the VDF scenarios. And so on. So what are the challenges we're facing today in MPC? So current techniques are kind of limited because basically all the practical approaches that we have an inherent overhead of multiplicative inherent overhead of some statistical parameter. We have some exceptions, but this is something that is basically in common to all practical approaches. And when we translate it into practice, this means that this employs an overhead at the least between 20 and 30x when we want to scale up to 100 parties. We don't have any implementations that go much beyond 100 parties. So what is the main goal, or our main goal in MPC? We want to design protocols where basically we can, or maybe compilers that compile passive to active protocols at essentially no cost. In practice, that means that we want the overhead, computation and communication to be very small. This is a very ambitious goal. I want to sort of even put a quantitative, like I want to make this overhead at most twice as much as the passive protocol. And as I mentioned, all the techniques, the practical techniques we have today are very limited. So we have to design or seek for new approaches. So this is just a quick reminder regarding the slides I had before, because OT is a very fundamental building block in MPC, both theory and practice. Oh, okay. Good. So, so what is a classic compiler that we have today is the GMW one. Let's recall this paradigm. So this is a very powerful concept that essentially compiles every semi-honest protocol, passive, into the malicious setting. And the way it does that uses zero-knowledge proofs, meaning that each party is proving at each step that the message it computed was performed correctly according to the protocol's instruction and some committed input and randomness. This approach is what we call, or follows what we call non-black box approach, meaning that as part of the statement and the witness, we need to sort of encode or hardwire the code of the semi-honest protocol. So basically, this compiler is non-black box in the semi-honest protocol. And in practical sense, it means that this protocol is inefficient, because when you want to implement it, okay, we have to embed this code, and different semi-honest protocols will give different efficiency measures, and this is very, very impractical. Essentially, this paradigm doesn't follow the black box approach we have in crypto, whereby when we say black box, we typically mean one of the following approaches. So we could either be black box in the functionality, like remember the example I had in the previous talk when we had an oracle to an OT functionality. We could be black box in a cryptographic primitive, meaning like PRG or PRF. And we also have very classic protocols like Garble circuits that are black box in this primitive. We could also be black box in some arithmetic operation or arithmetic gadget like a field or a ring. And the question is, can we come up with a black box alternative to GMW? So what would be the dream goal? Given a semi-honest protocol, we would like to design a maliciously secure protocol that accesses the semi-honest protocol in a black box way. It is possible for certain functionalities, for instance, for OT. We know how to compile passive to active OT in this approach using black box access. It is impossible for other functionalities, for instance, zero knowledge. If you think about it, what is a semi-honest zero knowledge protocol? If the prover is semi-honest, you could basically say, trust me, the statement is correct. How can you compile such a protocol into the active setting? So it's impossible in general. So I'm going to start with a very, very, very influential paper that's basically a follow-up to the Zero Knowledge from MPC paper I described before by Ishai, Prabhakar Manoj, and Amit Sahai. So I wanted to describe their compilation techniques and then describe follow-up works. So basically, we are kind of hoping to have the same evaluation process as we had in zero knowledge, right? Remember, we started with MPC, zero knowledge from MPC based on MPC-in-the-Head. These techniques turn out to be very practical and very influential and so on. We're kind of hoping, or we're in the process of having the same research direction and path also for MPC. Okay, so instead of having or achieving the dream goal, I'm going to describe a construction that combines two simpler primitives in order to achieve a much more ambitious goal. The two primitives are an honest majority MPC. This is what is called in the IPS paper an outer protocol. I'm also going to call it a virtual protocol. You'll see why in a second. And the second semi-honest two-party protocol, I'm going to explain it in two-party setting, but whatever I'm going to send is also extendable for the multi-party setting. So a semi-honest two-party protocol that could be described in the OT hybrid. These are much easier primitives or protocols to construct than an active protocol in a dishonest majority setting, and both exist unconditionally. Okay, so let's start with the outer protocol. So let me describe this protocol in a client-server model. So the clients have different role than the servers. The clients they have the secret inputs. They will secret share their inputs and will distribute the shares among a set of servers. And the servers are the set of parties that are in charge of the actual computation. After it is done, they will send the shares of the output to the clients that will reconstruct the output. Okay, so the number of servers that we will use will actually determine the what we call the error probability or the soundness probability of the compiler. And the requirements we need from this honest majority protocol is security against malicious or active adversaries, which is also adaptive. In the adaptive setting, the adversary may corrupt the parties throughout the protocol execution and not just at the beginning. We will have, we assume the adversary can corrupt at most one client, and a subset, a constant fraction of the number of servers. And typically in the honest majority setting where we have unconditionally secure protocols, we can also go all the way achieving fairness and guaranteed output delivery. These properties are not needed here because we are going to build a compiler for the dishonest majority setting where both of these, fairness and guaranteed output deliveries, are impossible to achieve in the dishonest majority setting. And another feature of the proof, we will require straight line simulation. So all of these are easy to achieve with classic honest majority protocol, especially a light version of the BGW protocol. For the inner protocol, remember I'm going to have two ingredients. The inner protocol, I'm going to use a two-party protocol in the OT oracle, with an OT oracle. And this protocol is very simple, is a semi-honest secure. For a technicality in the proof, we also need this protocol to be secure in the presence of adaptive corruptions, but sort of a weaker version, what we call the threshold is weaker, and also I can use, I'm allowing abort as opposed to, okay? And here, I need the semi-honest protocol, which is secure in the presence of an adversary that is sort of could make adaptive corruptions with erasures, meaning that we can have a setup where the parties generate some correlated randomness and then erase some of the randomness used for this process, and then the actual GMW protocol is executed, and this protocol is also secure in the presence of adaptive corruptions. So these are our building blocks. How do we combine them? And this is like a crucial slide on how to build or to design the compiler. So IPS sort of relies on what we call player virtualization. And that means that the servers or the parties in the outer protocol don't really exist. Their operations, their computations are emulated by the parties played in the inner protocol. And how do we do that? So this is basically, you can think of, you can take the honest majority protocol and think of it in a virtual sense. Since none of the parties in this protocol really exist, the two parties from the inner protocol need to actually emulate everything. So they basically are emulating whatever computation is done by each server. And the computation is essentially distributed. It's computed in a distributed way. So the state of these servers is split, and you can think of every computation as abstracted by a functionality, a reactive functionality, meaning the functionality goes in phases, like the same rounds in the protocol. And in each such round, each such phase, the input to this functionality are the views so far, which is shared among the parties from the inner protocol, and the state. And they run some protocol to compute the server's computation. And along the lines, there's a very, very, very interesting and important idea here, which is based on what is called the watchlist mechanism. They actually need to, not just the next message function, they actually need to compute the actual computation of the server. In a distributed way, yes. And of course, the next message function. Okay. Sorry. So this is done using DOT calls in the inner protocol. So let me be a little bit more precise. Maybe I could sort of switch to the next slide. So we think of the server's computation as a deterministic computation. This is typically the case in classic protocols, and we could actually achieve it with not a very high price. So, so what do we have? Each, in the outer protocol, each server has, he receives messages from the client, okay? It needs to compute something and then distribute messages to the client. And these are based on some secret state that is split. And as I mentioned before, you can capture this computation as a two-party functionality. If the server needs to perform an addition, this could be done locally, assuming that the secret sharing scheme supports addition. Now, if they need, or if the server is doing a multiplication operation, then we use OT to do the multiplication. Remember, these OTs are passively secure, okay? But our adversary could be malicious. So how do we sort of protect from bad messages? Like the OT is not really protected against any attack beyond semi-honest. So this is where the watchlist mechanism comes into play. Basically, you can think of it as a more sophisticated cut and choose. Remember, cut and choose, very, very roughly. You repeat a computation many times, and you test a subset of it. So here, essentially, the watchlist mechanism allows each client to watch a subset of the OT's computations done by the other client. This subset, of course, is oblivious in the sense that the other client doesn't know which OT's computations are being watched by the other clients, right? So, and by sort of assuming that by setting the parameters right, meaning that I can watch enough OT messages or OT computations, I need to make sure I don't violate privacy while still deterring the other party from cheating. This is like the great property achieved by Watchlist. So basically, each client will watch T/2 servers, or OT computations, where T is the privacy parameter of the honest majority protocol that we are using, the virtual protocol, right? So overall, we are not corrupting too many servers. Good. How do you actually set up this watchlist mechanism? So we're basically setting up watchlist channels where all the messages go through the channels, and each client has access to a subset of these. No. Let me get to that point. That's a very good question. Arpita is asking where do you use the fact that the honest majority protocol is actively secure? I'll get to that. All right. So basically, as I mentioned, all the messages, all the emulated messages going through watchlist channels, and these are implemented in the IPS paper. They use a one-time pad mechanism, like an encryption scheme that pads all these messages. And each client knows this padding for, say, T/2 of the channels. And then it could read or could see all the messages that go through these channels and check for correctness. And there it is implemented using wrapping OT. It could be implemented using T/N OTs, but it doesn't matter how it is implemented. The goal is to not letting each client learn too many of these padding values. Okay, so how is it? This is to answer Arpita's question. So as we said, each party watches symmetrically the other client. Each client watches the other client. And we basically have two cases. If a party tries to cheat too much, there is a high probability it will get caught by the watchlist mechanism. High probability one of the servers is cheating with will be on my watch list and I can actually detect the cheating. But catch and choose doesn't catch all the errors. It could be that with some probability, a client cheats with a small subset of the servers. And these are maliciously attacks, right? So how do we ensure that the overall protocol is still secure? This is captured by the active security of the honest majority protocol. So up to T corruptions, we rely on the security of the honest majority protocol. Above that, we will catch the adversary with high probability. Just as a side note, since we view the OT as OT oracles, and we want to make sure that a party is consistent with respect to the input and output to these OT calls, we rely on a reduction from OT to random OT, where the OT's input and outputs are random and then reduced to the actual OTs. And the reason is that we want to protect against what we call selective attack. It could be that the adversary is getting caught, but still learns something about the input or the output to the actual OT. So with probability half, it will get caught. The OT is executed on random inputs. And then no leakage is caused. And by repeating this sufficiently many times, we ensure that the soundness error is small enough. That's basically the idea. Okay, I'll just say maybe just a few words about simulation. Basically, it follows similarly to how we prove composition in MPC, where we compose two protocols. Here we want to compute or to define a simulator for the inner protocol. And for that, we are going to use the simulator for the outer protocol. So the inner protocol, remember, is a semi-honest protocol. And it can actually detect whenever the adversary is cheating through the watchlist channels. So whenever an adversary in the inner protocol is cheating with respect to some server's computation, this server is being corrupted. This is why we need adaptive security, because it could actually happen throughout the protocol execution. So you corrupt this server and you have access to its input and output. I mean, this is what the internal protocol for the outer simulation is given. And at some point, so the inner simulator is sort of calling to the outer simulator. And if the protocol, the inner simulator, is cheating, it could be able to sort of corrupt the corresponding party. So this is just a high-level way to construct the simulator. And this gives a new compiler, which, given a two-party functionality and an honest majority protocol for computing this functionality, a semi-honest protocol, two-party protocol, for computing the reactive functionality that captures the computations of the servers, we essentially combine them in a way that gives us a new two-party protocol with active security that makes only black box uses of the two underlying protocols, both the honest majority and the semi-honest one. Remember, black box is an important feature to get practical efficiency. And that's the strength, the power of this paradigm, because you can actually plug in whatever building blocks you want, and you can get active security, okay? Specifically, you can compile any semi-honest protocol to an actively secure protocol. And this generalizes to an arbitrary number of parties. So that's a great paradigm. It gives us an alternative, a black box alternative to the GMW compiler I described before. It is very flexible. You can get new black box constructions, new constant round constructions. Really, it's like sort of a fantastic tool to be used in MPC. And now the question I'm asking is, what about concrete efficiency? Specifically, is MPC-in-the-Head concretely efficient, and can it compete the current state-of-the-art practical constructions that we have? So remember, the goal is to combine two building blocks into active security. This approach achieves great asymptotic efficiency, even constant rate asymptotic efficiency, but only for a small number of parties. And the concrete efficiency of this paradigm was actually studied in a follow-up paper by Lindell et al., which observed that the bottleneck of this approach is inherent by the number of servers that are used in the virtual protocol. The more servers we have, the less concretely efficient the overall protocol will be, because we have to emulate more virtual parties, which makes sense. And now I want to tell you about a follow-up work that is joined with Yuval and Mutu and Antonio Mercedon, that shows how to make this approach practical for two-party arithmetic computation. So, as opposed to Boolean circuit, which is sort of in the center of most of MPC protocols, arithmetic computation is performed over a larger field. And it has many, many useful applications as well, like in threshold cryptography, pattern matching, neural networks, statistics-based computation, and many more. And as a generalization of OT, here the atomic building block is what we call OLE, Oblivious Linear Evaluation. So the parties' inputs are over some field F, and the goal for the receiver is to learn the linear combination, a linear combination or linear function of the sender's input and its own input. And if you sort of stare enough time, you can see that this is a direct generalization of OT. So what do we know, or what did we know up until that point? For arithmetic computation, we basically had three different methods for secure computation. The first one operates in the OLE hybrid, right? The parties have access to an OLE functionality. And here, the best protocol was due to a protocol called TinyOLE, which is as well an extension of another important protocol called TinyOT, which also uses OLE in a black box way, but the number of calls it makes per gate is 22. 22 OLE calls, where security relies on the fact that the OLE must be actively secure. I think by now they actually even managed to reduce this number, but they need active OLE. Another approach is to use OT, also in a black box way, in the OT hybrid model. Here the disadvantage is that if we want to reduce OLE to OT, we need bit decomposition. So complexity grows linearly with the field size. Finally, the third approach which is based on semi-homomorphic encryption schemes, which is a weaker primitive than fully homomorphic encryption. There, typically, it sort of follows a similar approach to GMW, where they use OLE to generate random triples or authenticate random triples. And then they sort of apply a zero knowledge on top of it to ensure that the computation was done correctly, where all these semi-honest encryption schemes are come from the lattice word. So the zero knowledge must be, I mean, all the OLE and the zero knowledge construction must be lattice friendly. And typically the parameters are very large, and so on. Good. So I'm returning to the main question we sort of asked. Now I'm being a little bit more precise. And we want to know what's the overhead of achieving active security given only black box access to an OLE, but not just OLE, we want passive OLE. We're very ambitious, not active OLE. We want active security, we only have access to passive OLE. Okay, so let me just spell out the result, the main result in this paper. We designed the first two-party protocol that makes constant number of calls to passive OLE per gate or per multiplication. For nice circuits, nice, I mean, wide enough, this constant is as small as 2. Remember, that was our concrete goal from before. As a use case, as a concrete use case, we show how to build active OLE from passive OLE, where the number of calls made is only 2. So the overhead from passive to active is just 2 in communication. And just to compare previous work, remember, it was 22 calls for active OLE. And we do know how to compile passive to active with a similar overhead, but this is only for a very specific OLE construction based on a coding-based assumption. Good. I want to illustrate very quickly how this is done in the MPC-in-the-Head world. So remember, I mean, now I'm extending it to multiple executions of OLEs. I'm running many OLE at once. So the parties have their inputs, and then the first phase, what they do, they sort of encode it using Shamir secret sharing, packed secret sharing. They encode these inputs, and they send them to the virtual servers. Send them, right? I mean, the servers do not really exist. Everything is secret shared amongst the clients. These servers basically compute locally the OLE computation, right? Since it is a linear computation, you can do it locally. And then we run some tests. And here we sort of extend the analysis from the previous talk, from the Ligero paper, to the two-party setting. We run similar tests of, for instance, we need to, as the first test, we need to check that the encoding was done correctly. So we get some randomness from the clients, and we do something similar, taking a linear combination of all the shares, spreading them back to the clients that check that test that this was done correctly. And this, again, relies on an extended analysis from the Ligero paper. Finally, after we run all our tests, the servers simply send the output to the client, to the receiver in this scenario. Remember, only one party learns an output, which decodes back the output. So this is basically a very, very high-level illustration of how to perform many OLEs in parallel in the MPC-in-the-Head approach. So just to sort of conclude this work, our protocol inherent the flexibility of MPC-in-the-Head and can be plugged in with any OLE instantiation. Take your favorite OLE, lattice-based, coding-based, anyone. And you can plug it in, getting different trade-offs. It doesn't need to be zero-knowledge friendly like in the fully homomorphic encryption-based approach, because it doesn't have to rely on lattices, and it's black box, right? We don't need to know the code or rely on knowing the code of the OLE. And basically, you can plug in any off-the-shelf implementation, software implementation. A bonus feature of this is like a great feature of these compilers. We don't really need to start with a fully secure, semi-honest protocol. We can even relax these requirements, starting with some protocol that embeds some error, either correctness error or privacy error. And then the compiler will fix this error. On the way to achieving active security, we will also boost the security of the inner protocol. Why is this such a great feature? Because constructing semi-honest protocol with tolerate that has this error could greatly affect the practicality of the OLE construction. For instance, lattice-based OLE constructions are so much more efficient if you tune the parameters that allow privacy error, for instance. So this is a fantastic feature of this type of compilers.
What is the minimum number of active OLEs that create to kick in this?
You mean to get the overhead too? I think it was to the thousands. I don't remember the exact number. I can check, but it was to the thousands. I mean, a few thousands. Oh, well, have you set the parameters of the underlying honest majority protocol, right? So you have a robustness parameter, a privacy parameter, and you have like a formula to get soundness error. So you play with the parameters. Basically, number of servers. That's.
So is it better in the previous specific construction?
What previous?
The previous passive to black to white, which works for a specific construction. Yes, boss.
You mean how many? I don't know. There is not amortized, I think. There is like you could, even for a single execution, the overhead is 2, I think, yeah. But that's a good question. I don't remember. I can check and tell you. Okay, good. So I don't think I have too much time. The clock is not set for some reason. So, but
it's okay. You have definitely 15 minutes.
Okay, good. So in the last part of this talk, I want to tell you about recent work with Muthu and more Weiss. And so in LevioSA, for instance, that protocol worked only for 2 parties. And the next natural question is to ask, how can you extend it for more than 2 parties? So let's try to, so this is the paper, the title of the paper. And let's try to understand the inherent bottlenecks in the IPS framework. Because I mentioned before, it does get great asymptotic efficiency, but only for a small number of parties. And why is that? So first of all, the main bottleneck, as I mentioned before, is the watchlist mechanism. Why is that? Is that because the number of watched servers should be order of some statistical parameter. So we can actually claim that with very high probability, the adversary cannot cheat too much. But now every party needs to choose its own subset to be watched, right? So increasing the number of parties in the protocol, participating in the protocol, means increasing the number of watched servers, meaning increasing the number of overall servers, right? Because the overall number of watched servers still cannot cross some threshold of the underlying outer protocol. Remember, this should still be in the within the bar of privacy, the privacy threshold. So that means we need overall more servers. So inherently, that means that we have this, we sort of have this statistical overhead when we use the watchlist mechanism. Good. So that was our first starting point when you started this project. We want to avoid using the watchlist mechanism because it's expensive. So what do you do? So this approach was sort of used in different other protocols. Compute first, check later. What does it mean? It means sort of you can run the computation and check only at the end before you reveal the output. Great. But what's the problem here? Why wouldn't it work with the IPS framework? Because we are using a semi-honest inner protocol, right? So we can't just check at the end, because by then, the adversary can sort of violate the privacy of the other parties completely. So we can't just do that, right? This doesn't work as is. Okay. Another problem we had is what kind of outer protocol to embed. So in IPS, one of their, the contribution or the result of achieving good asymptotic overhead was based on the Dumgarty-Shai 06 protocol as the outer protocol. This is an honest majority protocol. And that was used as the outer protocol. But again, we are after scalable protocols. And this protocol did not scale as well because of the way it was constructed. So we sort of ran into all these limitations. And we had to think a little bit different and not use IPS as is, but sort of tweak it a little bit. So first of all, we carefully designed our honest majority protocol to be used in our new compiler. We started with the BGW. BGW is not enough. I mean, you need to use packed secret sharing, but it doesn't matter for the sake of this presentation. So you start with this protocol, and you basically want to combine it with an inner protocol, but we abstracted away. So remember before I always sort of described the protocol in the OT hybrid, in the OLE hybrid. But now I am talking in the F-mult hybrid. So think of F-mult as a sort of functionality that computes a multiplication. So we have secret sharing among the parties. And we want to compute a multi-party functionality that generates the product, the shares of the products of the combined value of the two parties, of the multi-party. And it's more useful to work this way because this captures many other protocols that were not considered before. So previously, it was very useful to think of in the OT, hybrid, and so on. But we have other useful instantiations for fmult. For instance, based on homomorphic encryption. So now you could actually plug in any such instantiation into a protocol. Now, the third bullet essentially is the crucial one. So how does it work? Before in IPS, we had only one layer of secret sharing. Remember? Basically, we had additively secret sharing of the internal state of the service, and this is how the parties sort of evaluated and computed the circuit. Now we have two layers of secret sharing. We have the layer of the Shamir secret sharing in BGW. Each such value is then additively shared among the parties. So what does it mean? It means that every party has a global view of what's going on in the entire protocol. Again, two layers of secret sharing. You start with Shamir secret sharing, and then you additively share all these values. And now, this brings us to another optimization. In all the honest majority protocols, in some way or another, when we compute a multiplication gate, typically it is done by taking two Shamir shares, multiply them together. So if we start with two shares that correspond to a t-degree polynomial, now the degree of the multiplied shares is increased, right? Now it's 2t, meaning I need more shares to sort of reveal the secret. And now we need to perform some protocol that is called a degree reduction. And these protocols are typically expensive, and they form another bottleneck in the when we want to sort of emulate them. So now the fact that we switch to two layers of secret sharing, we could actually do the degree reduction locally because it is involved of linear operations. And since every party has a share of a global view, each party can actually sort of compute a share of the outcome of a degree reduction. So no need for communication. So let me just sort of summarize our results. We managed to get, our inspiration was IPS. We identified the bottlenecks in IPS, and we managed to sort of overcome them in order to design the first protocol that achieves constant communication overhead over passive GMW. So since we sort of abstracted our inner protocol in the half-mile hybrid, it fits into any framework, both the dishonest majority or the honest majority settings. And you can actually achieve constant overhead throughout all settings. Where in the arithmetic setting, we extend what we had in LevioSA, the analysis from LevioSA, the two-party protocol, and can get as overhead as small as 2. for sufficiently wide circuits. For the Boolean setting, the constants are unknown and to be explored because the protocol makes or uses heavy machinery like AG codes. So this is a lot to explore and understand in terms of the concrete efficiency. But this is one step further. And with that, I will conclude. Thank you. People are reading the slides, so no one is.